All right, everyone, welcome. Today we are pleased to have Ryan Endsley giving our colloquium. So Ryan is a fellow alum of Washington University in St. Louis, where he got his undergraduate degree. Then he got his PhD at University of Arizona in 2022, where he was working with Dan Stark, and has moved on since then to be McDonald Observatory postdoctoral fellow. Ryan works on, as we'll see, a variety of topics in the first billion years, including the nature of star formation, the growth of supermassive black holes, and mapping out the process of reionization. So take it away.
All right, thank you very much, Drew. And thank you all for joining. So as Drew said, I have been pushing hard over the past couple of years to figure out what JWST is telling us about very early galaxy assembly, reionization, supermassive black hole growth. So that's going to be largely what my talk is focused on today. So just to start off, some introduction you all are probably at least somewhat familiar with. Cosmological framework, the universe happened, Big Bang. The universe was very hot and ionized, right? And then inflation happens, the universe expands with time, the universe cools down, everything becomes neutral. But we see the universe is ionized present day. So something had to happen in between there. We call this hydrogen reionization. And this is when we believe basically galaxy formation had a large-scale cosmological impact. So reionization really is the imprint of galaxies first forming, producing high energy light, and ionizing nearly every single hydrogen atom in the intergalactic medium. So in that framework, I want to emphasize here that the questions that we want to answer about galaxy formation and the questions that we want to answer about reionization are not independent, they are heavily intertwined. These are not two independent processes. They had dramatic influence on each other. So here I'm just highlighting a few of the questions from each category, okay? These are by no means all of the questions in these very large topics that are pervading a lot of people's careers. But the emphasis again here is that whenever we want to understand reionization, we need to understand galaxy formation. Whenever we want to understand galaxy formation, we can use what we learn about reionization to better inform that as well. So first question, when did reionization happen? I'll go over this very briefly, but just in a nutshell, you can use the absorption spectra of high redshift quasars. They're sensitive to the Lyman alpha, Lyman beta force. Tells you something about the amount of neutral hydrogen in the intervening intergalactic medium. And what studies have told us over the past couple decades, and really, I think, cemented in the past couple of years, is that reionization ended around redshift 5.3. So the universe was, again, nearly fully, completely ionized around redshift 5.3. That's about 1.1 billion years after the Big Bang. We can also use information from the cosmic microwave background. So the Thomson scattering optical depth to the CMB tells us the total number of free electrons, the column density of free electrons to the CMB, gives us some constraint on the timeline of reionization as well. And what that's telling us is that reionization was roughly halfway complete around redshift 7, 8. So it's about 700 million years after the Big Bang. So this is the timeline that we're working with. Greater than redshift 5, halfway complete around redshift 7 to 8. Who necessarily knows when it began? That's a whole other question that I won't really touch on here. But let's focus on the redshift greater than 5 part. So what caused reionization? Well, whenever Hubble, was taking all these wonderful imaging surveys, deep imaging surveys over the past few decades, it led to the discovery of over 1,000 what we call Lyman break galaxies at high redshifts. These are just UV selected systems, star forming. At least that's what we thought by and large. It still seems to be the case by and large. But there were over 1,000 of them, and they really pop up whenever you look at deep fields. And you can do the simplest kind of experiment possible. You can count the number density of galaxies as a function of their UV luminosity or absolute UV magnitude, and you'll get a plot that looks like this. So over here is your bright end, and over here is your faint end. And the key point here is that at high redshifts, redshift 6, 7, 8, what have you, this is a very steep faint end power law slope. So you have far more faint galaxies at high redshifts than you have brighter objects. Knowing that, people have for a long time thought that this dominant, very abundant population of faint galaxies at high redshifts were likely the dominant contributors to reionization. That has been kind of the main idea and tossed around for much of the past 2 decades or so. But really, that is kind of a number density argument, and a number density argument alone. We have very little information on the properties of these very faint high redshift galaxies prior to James Webb. Some of the questions that we wanted to answer are, how rapidly are they assembling their stellar mass? What are their metallicities and dust content? And really, what are their ionizing properties? How efficiently were they able to produce ionizing photons and then leak those ionizing photons into the intergalactic medium? And this was just a very, very hard, if not impossible, set of questions to try to answer prior to James Webb. And I want to just quickly show you why. So here is an example of a redshift 7.5-ish galaxy. It's moderately faint. It's not super faint by any means. But nonetheless, in typical deep HST fields, what you would usually get is, a 3 to 5 sigma detection in your HST bands here in the rest UV, and then nothing over here in the rest optical that was probed by Spitzer IRAC. This is our really only window into the rest optical, but it largely resulted in non-detections because Spitzer had a really small mirror. It was just, several decades, technological, improvements were made with James Webb, obviously. So what we had then is these types of galaxies where you could fit, this kind of spectral energy distribution that's showing here in red. And this is a model where the galaxy is relatively old. It has been forming stars for 500 million years. And it has a relatively high stellar mass, 1-ish times 10 to the 9 solar masses. So just pushing beyond the nominal dwarf galaxy regime, okay? And this is entirely consistent with the data. Sure, maybe that's what this galaxy is. You can also fit this data with this model, where now I have light that is completely dominated by recently formed O stars. Okay, it's a very young, light-weighted system. You're seeing the Balmer jump from nebular continuum emission here, and then signatures of extremely strong nebular line emission boosting this photometric band above the continuum. But the light-weighted age here is 3 million years. And it's, again, completely consistent with the data, just like this one was. Even though here, this is a stellar mass 1.3 by 10 to the 9, and this is a stellar mass about 3 by 10 to the 7. So our uncertainties on stellar masses of faint high redshift galaxies were tremendous. Our uncertainties on their ionizing properties were also tremendous prior to James Webb by and large. So again, going back to the key questions that we want to try to answer here, we want to understand reionization. We want to understand early galaxy assembly. The UV luminosity function, that is just number density of galaxies as a function of UV luminosity. This has been, for more than a decade, our primary way of just kind of constraining what happened in the early universe as far as galaxy assembly goes. So we want to know, what are the demographics of galaxies at the bright end? And then what are the demographics of galaxies at the faint end? What we could do prior to James Webb is we could begin to characterize the brightest galaxies in the early universe. So my thesis a few years ago was largely devoted to using this deep ground-based and Spitzer imaging over 7 square degrees of the sky. Compare that to a typical, HST deep field of 0.1 square degrees or smaller. You're getting a much larger area. You're able to sample the bright end of the luminosity function much better. And we found over 100 of these UV bright systems, so J-band magnitudes around 25, 26. So let's see what this Spitzer data told us for these objects, told us about these objects. So what we often found was, this flat UV continuum. But then in the rest optical, where we really had long struggled to characterize these objects, we were seeing these kinds of color patterns. So what you're seeing here is this photometric band is being driven up to higher fluxes because of extremely high equivalent width O3 and H beta emission. And this other band gives us the rest optical continuum down here. There's no other way you can make this kind of color pattern. You can't do it with a Balmer break. It has to be due to this extremely strong nebular line emission. And it wasn't just in one galaxy, it was in several. Okay, we found O3 H beta equivalent widths rest frame, 2,000, 4,000, 1,500, these kinds of equivalent widths just are not really at all ever seen at low redshifts. And here now I'm giving you a sample of, several tens of high redshift galaxies, and I'm finding a handful of these objects in that sample. So really what this is telling us is that, there is a dramatic evolution in the nebular line properties low redshift galaxies that we've long been used to now the UV bright objects that I'm able to actually characterize with Spitzer. And what does that mean? So first, let's think about what it means for galaxy assembly. The way you get such a young light-weighted SED is by having a huge, very recent upturn in your star formation rate. Suddenly now the light in your galaxy is just completely dominated by hot, massive O stars. That's how you get this kind of bomber jump plus the extremely high equivalent nebular line emission. And this is just, an inferred star formation history here of one of these galaxies. And you just really can't even see, the time scale in which the star formation rate rose by more than a factor of 10, okay? Let's also think about what this means for reionization. So these galaxies have recently formed a lot of O stars, very high upturn in star formation rate. And what that means is that they're very efficient at producing hydrogen ionizing photons. So the rate at which hydrogen ionizing photons are produced is given by this term psi ion times your UV luminosity. So studies at low redshift have shown that this ionizing photon production efficiency, psi ion, increases as you increase your nebular line equivalent width. This just makes sense. A larger fraction of your light is dominated by O stars, so you're going to have stronger nebular line emission. You're going to be producing more hydrogen ionizing photons. No huge surprise there. So this suggests, this was a really nice first glimpse, that perhaps these reionization-era galaxies were very efficient ionizing agents. But it's not only their production that was interesting here. It's also perhaps the case that these very early galaxies were efficient at leaking those ionizing photons into the IGM. Galaxies are full with lots of neutral hydrogen. The ionizing photons need to get out of the interstellar medium and out of the circumgalactic medium to make it into the intergalactic medium to actually cause hydrogen reionization. And that's a hard problem. Galaxies at low redshift are often very, very inefficient at doing this. But what we think happens is that whenever you have very efficient stellar feedback, radiative winds, what have you, then perhaps these ionized channels are carved out through the ISM and CGM of galaxies, and then you can have sight lines with very efficient ionizing photon leakage. And here's just one such example of an object with high O3 H beta equivalent width at redshift 3.2, and it has alignment continuum detection. Okay, it's kind of supporting this claim. There's been several other works, kind of arguing this is the same case. And then there have been other works showing that you don't always need strong nebular emission to power efficient alignment continuum leakage, but it does seem to be at least one of the properties that we knew of a few years ago that did suggest that things might be efficient at getting ionizing photons into the intergalactic medium.
Brian, could you just put some context on the escape fraction? Is this like what it is?
So Alan just asked a question, can you put this in context of the ionizing photon escape fraction? Yes. So this object, I believe here, had an ionizing photon escape fraction of 10 to 20%, somewhere in that range. Whenever you talk about galaxies that are redshift 2-ish, people usually find ionizing photon escape fractions of much lower, 1-3% at best, right? Generally speaking. So if a lot of high redshift galaxies have these kinds of properties, maybe they're all somewhat closer to 10-20% than they are to 1 to 3%, just making reionization easier. Yeah.
So when people were using percents for this redshift range, get some sort of thing about the slope, or sort of right ballpark with that much detail.
I think they were roughly in the right ballpark. They had to be, though, in order to make reionization happen in their models. Yep. So I think we've always been kind of limited into a regime where the ionizing photon escape fraction has to be at redshift 7-ish, has to be higher than what we usually see at redshift 1 to 3. Yeah. Okay. So just to recap again, at the very bright end of the UV luminosity function, the regime that we were able to characterize with Spitzer, we found extremely high O3 H beta equivalence, very strong nebular line emission. And that meant very recent strong rises in star formation rate. efficient ionizing photon production, and perhaps efficient ionizing photon leakage into the intergalactic medium. But again, the key point here is we really need to characterize the very faint population, because that's a far more abundant population. That's a population that people had for decades assumed were the primary drivers of reionization, okay? And this is where JWST comes into play. So what I did last year is I used data from the JADES GTO survey to characterize the entire sample of Lyman break redshift 6 to 9 galaxies that I identified in that survey. So there were 756 galaxies in total. It included hundreds of these very UV faint objects. So these are, in the histogram here of absolute UV magnitude, that's these shown in red. These are objects that were previously only really identifiable in the Hubble Ultra Deep Field, or in lucky cases behind some kind of lensing field, okay, with high magnification. But now we have hundreds of these. We have a statistical sample. And what's really important here too is that JADES gives us 5 imaging bands in the rest optical. Remember, Spitzer only gives us 2 bands. 2 of the 5 bands in JADES are medium bands. Medium bands are much more sensitive to nebular line emission than broad bands are. Okay, so this really allows us to start piecing together, the rest optical properties of faint reionization-era galaxies. So this is just an example of one of those, very faint galaxies that we found in the JADES survey. So this is 29th magnitude for reference in the UV continuum. But you can see the signatures of extremely strong O3 H beta here, and then also H alpha here in F44W. And then this medium band on here, F410M, is giving us a nice, relatively clean probe of the continuum. Okay, so you have some really nice, far better than we've ever had before, constraints on the SEDs, spectral energy distributions of these galaxies. We found several objects that were like this at the very faint end, showed these young continua and very strong nebular line emission, but they were not as common as what we found at the very UV bright end with Spitzer IRAC, and also validated with the sample that we had from the JWST data. Okay, we have more bright galaxies. I can verify all the stuff that I did in my thesis. So the fraction of galaxies with extremely strong O3H beta emission, we're about 1/5 to 1/4 at the bright end, and then we're getting down to less than about 10% there at the very UV faint end, okay? So what's going on here? There's a new type of spectral energy distribution that now seems to emerge as we get down to the faint end of the UVLF at redshift greater than 6. So here, I just really want to walk through one of these in detail so we're all on the same page, so please bear with me. Here's a galaxy, so 28th magnitude, pretty faint. You see here this pretty flat rest UV continuum, and then we have that medium band anchoring the rest optical continuum, telling us that there's not really any Balmer breaks. So we have a young continuum. Then I have these 2 bands that are nicely telling me what the equivalent width of the O3H beta emission is. So you'll recall that in the UV bright population, I was finding typically objects greater than 700 angstroms. Here's an object with a young continuum, but then weak O3H beta, relatively weak, 400 angstroms. Okay, was not expecting this. So how do I explain this? I have a young continuum, but it seems to be that I'm lacking the ionizing photons that I would expect that would power the strong O3H beta emission. Okay, why is my O3H beta not as strong as I thought it might be? One possible explanation is that maybe these galaxies have extremely low metallicity. That's maybe not that surprising. You go down to the faint end, you're going to find relatively, infant galaxies that just aren't metal enriched. So you can maybe explain this with, a metallicity solution of 1% solar metallicity, so very metal poor, right? If that were the case, you would expect relatively strong H alpha emission. Lower metallicity means lower stellar opacity. You get more ionizing photons getting out. Hydrogen recombination doesn't care about what is going on with your metals in your galaxy by and large. So if that were the case, if this extremely low metallicity were the case, I would be predicting an H alpha equivalent with around 1,000 angstroms, and that would drive up a pretty strong excess in F44W. Do I see that? No. So now the data is giving me this about 4 sigma offset from the model prediction in this constant star formation history model, which is what everyone has been doing for several years. We're finally maybe getting around to not using that, but that's where this narrative is going. The main point is that these constant star formation history models are inconsistent with the full NIRCam SEDs of some of these UV faint galaxies. This isn't just one object in the sample, there are several. So I'm just going to flash through to really emphasize that with the JADE sample, this fairly large coverage with JWST imaging goes very deep, gives you lots of medium bands, that you can really start building up a statistical sample of these types of objects to really convince yourself that there is something that in the data that is telling us that these models that we have long been using no longer work. So here's another one where I get tension with the data. You can see it's not just here, but it's also several other bands. It just doesn't really work. There's another object. There's another object. Another object. Here's the last one I'll stop on. Okay, so this one, very UV faint, 29th magnitude. It's predicting an H alpha equivalent of about 1250 angstroms in the constant star formation history model. Since I put this paper out, we now have a spectrum of this object with NIRSpec. So now I can validate, okay, was there just something wrong with my photoionization modeling, or is the data actually reliable here? So here's that galaxy. Here's the NIRSpec spectrum. So we see, again, no significant Balmer break. We do see both O3 emission here and H alpha emission here, but they have both relatively weak equivalent widths, so about 400 angstroms. And you'll recall from the constant star formation history modeling that it was predicting 1200 angstroms. So clearly inconsistency, still again with the spectrum from what these constant star formation history models are trying to suggest here. Now let me just go through that again a little bit more clearly. Yes. Here. Yes, yeah. So the 400 angstrom equivalent with H alpha emission isn't going to boost that band that much. So again, this is the constant star formation history model SED. The better SED looks a bit bluer, so the continuum drops closer to where this band is, and so it all works out. Yeah.
The SED plus in nebular emission models assumed for escape fraction? Great
question. Do you mind if we hold off on that until the end? They assume 0. So the question was, what are the photoionization modeling assume for ionizing photon escape fraction? All this assuming F escape equals 0. But I do have some backup slides to address that issue if we can wait until the end on that. Good caveat to keep in mind, everything I'm going to argue about Bursty star formation history is a little bit degenerate with the assumption of extremely high escape fractions of ionizing photons in some of these galaxies. But I'll get to that at the end. All right, so here we have the galaxy again, the NIRSpec spectrum. I'm just showing you the data. This is what I get whenever I fit that constant star formation history model. Okay, it really wants to latch on to the strength of the O3 emission because it's the highest signal to noise detection. But whenever it does that, it drastically overpredicts what it thinks the H alpha emission will be because it's expecting tons of O stars in this object, lots of ionizing photons coming out. You can also see that it's inconsistent with the rest UV slope over here. We saw that in the NIRCam data too. It just wasn't matching the full SED, but you see that again in the spectrum. Okay. Here's what I get whenever I fit a model with a flexible star formation history. All I had to do was just allow the star formation history to not be constant, and then suddenly we get full consistency with the data. It matches all the lines, it matches the continuum. Every single piece of data I have on this object tells me that a flexible star formation history model with 0 ionizing photons leaking out does, successfully reproduce everything I have on this. And that's not just for one galaxy, it's for several. So you can see here, these are the ones that I flashed through a little bit ago. But in every single case, now I'm footing with models of flexible star formation histories, and they do a much better match to the photometry. I don't have spectra of all these. Yes, Gwen. Okay. I think that's good. Yeah.
I have no problem whatsoever with you using flexible star formation history models, but just for the sake of argument, I'm curious, what parameters does your model allow you to change about the nebular conditions and the metallicity in order to attempt to fit? Because if you have O3 over H alpha is sensitive to a lot of different things about the nebular gas conditions and its metallicity. And so, like, what flexibility do you have in those changes, or is it just some fixed model and then you're just changing the star formation history essentially?
Okay, so the question was, what changes are you allowing in the nebular conditions, not to the star formation history? So we allow for changes to the ionization parameter. This is all done using the Gutkin et al. 2016 photoionization models that are in Beagle. So these are single star models. They're not no binary implementation here at all. And we allow metallicity to go down to a bit less than 1% up to half solar. So quite a large range there. And then we also allow the dust to metal mass ratio to vary as Beagle allows us to do, and that gives a tiny bit of flexibility, but by and large, it's the ionization parameter and the metallicity, as you were saying, that governs all this, right?
And it's solar scale.
Yes, yes, solar scale abundances, yeah. And I mean, you know, all the photometry is really telling me is something about the oxygen abundance through O3. There, I don't have really any actual constraint on nitrogen abundance or anything in the photometry.
Do you know what for like density or pressure?
I believe the electron density is 100 per cubic centimeter. Yeah, which may be a bit small, but yeah, there have been some JWST work suggesting that, at least for some objects, that's not a ridiculous assumption. Yeah. All great questions. Thank you. So we no longer, with all this, you know, framework of bursty star formation and everything, we no longer allow or require, sorry, extremely low metallicities to explain the weak O3 emission that we were finding in the objects with young continuum weak lines. Okay, just allowing for flexible star formation histories does all that. So here's the way this all works: is the objects with young continua, relatively weak lines. I had a burst of star formation about 10 to 30 million years ago, and what that gives me is a lot of B stars that are still around to give me the young continuum. But because the star formation shut off, you know, somewhere around 3 to 5 million years ago, I am missing a lot of the hot massive O stars that the constant star formation history models expect that would lead to the very strong nebular line emission. If I remove all those hot massive O stars, suddenly my emission lines weaken considerably, and then you get full consistency with the data that we have on hand. I want to emphasize here that the extreme light emitter population that I've been talking about, that we found with Spitzer and everything, they implied bursty star formation histories as well. Because as I said at the beginning, you need to have this sudden strong upturn in your star formation rate over the past 3-ish million years in order to give you thousands of angstrom equivalent width nebular emission lines, okay? So what I think is happening is that these young weak line emitters shown here are just the flip side to the coin of the objects with the extremely high equivalent width nebular line emission. So these are objects that are currently experiencing the burst. These are objects experiencing, you know, kind of a lull or napping mode, off mode, whatever you want to call it, okay? But I think we are seeing, you know, the actual different populations in different stages of bursty star formation histories at early times. It's also important here to emphasize that my work is not the only one by any means addressing this at high redshifts. There have been several papers, including from Alan, over the past couple of years using JWST data to really provide, I think, the first hard-hitting evidence, empirical evidence for bursty star formation histories in the reionization era. Okay. And what's
by using this broader data, it's sensitive to A stars, which were also made at the same time. But the interval of the A star population that comes from whatever burstiness there is in hotter young star. So instead of just looking at the balance of the radiation in the emission lines, and I've measured those, of course, is what fraction of the light are they responsible for, but the same using those medium bands. But in this case, we're integrating a bit of fraction of the billion years instead of all this activity. I mean, both completely consistent, but it's good to know that these very different indicators of what the stellar population is doing both imply that it's a very versatile.
Yeah, so just to reiterate what Alan said, Alan was using largely broadband photometry, so he was sensitive more to the Balmer breaks in these objects, right? And you don't necessarily need to generate a Balmer break from long time constant star formation, right? So you can generate a kind of a post burst, but in general, just that strength of the Balmer break gives you some kind of integral constraint on the star formation that has happened throughout the course of the galaxy, and you're limited by how long the galaxy has been around by its redshift. So it all can kind of give you complementary constraints, as you said, on the star formation histories of these early galaxies. Yes. And there have been other works here, Lucer et al. And Victoria Strait et al. That have looked at this and spectroscopically selected galaxies that kind of show that you can't, they're just inconsistent with constant star formation history models. Okay, so that's all the observational side. I want to emphasize here that Bursty star formation histories are really just expected in every high resolution, radiative, radiative simulation at early times. So here I'm just showing you some example star formation histories down here from the fire simulation, up here from the Sphinx simulation. But you can see that they're predicting, if you look at the black lines down here, variations in your star formation rate that is greater than a factor of 10 on less than about 30 million year timescales. Okay. If you look at the Sphinx simulation, it's a little bit longer cadence and smaller amplitude, but the bursty nature of these high redshift galaxies is nonetheless present in the simulation as well. So the exact cadence and amplitude of the burst depends on the models. Some people have done this with analytic models as well, in addition to the simulations. And I include some there, but I just really want to highlight the point that this is really expected, but it's nice to see, nice to finally have the data to tell us, that there's evidence for this in high redshift galaxies. Something I want to really highlight here is that whenever you have galaxies with very bursty star formation histories, so strong variations in star formation rate on 30 million year-ish timescales, you will get strong rapid changes in your UV luminosity at fixed stellar mass. Okay? So here I'm just showing you some tracks in UV luminosity. Here is an apparent magnitude at redshift 6 for reference, if you're more familiar with that. And this is the time since the burst. So if I just have a burst with a mass of 3 × 10⁷, you can shift this up and down if you change that. But if I have that burst mass and I turn it on, there's some Wolf-Rayet phase here, but it's around 26-ish mag observed in around 1 to 3 million years after the burst. And then if you only go 30 million years, then suddenly you're down here if you have negligible star formation after the burst. Okay, so the galaxy can drop by 3 magnitudes in apparent brightness whenever you just shut off star formation, or at least make it negligible, for only 38 million years or so. And that's exactly, if I go back here, kind of what at least the fire simulation was predicting for some of these galaxies. It's important to note that, the light to mass ratio of a main sequence star goes to this relation. So the hot massive O stars that are produced shortly after burst have huge light to mass ratios. Okay, that's effectively what's driving this. Yes. This is with no binaries. That is correct. So if you implement binaries, let's just address this. If you implement binaries, then you would expect your rejuvenation kind of processes as something that people have predicted, where some of the mass from the secondary star flows onto the primary star and just kind of gives it more mass and lets it shine brighter longer effectively. That can happen. I think there's perfect reason to believe it does. But if you allow that, then that's going to extend the time over which you have strong nebular line emission, and it's going to extend the time at which you stay bright in the rest UV effectively. Again, I think that's possible, but then we have objects spectroscopically confirmed at redshift 7 that show no nebular line emission at all. And then how long does that imply it's been quenched if you invoke binary synthesis models? I don't know. But yeah, so I think there's a lot of room to think about what the binary evolution models imply for some of these objects, but then it does get kind of messy to think about what the timescales are. I think just assuming that there's not a huge impact, then you get this 30 million year-ish timescale that we're working. Yeah, and I think, IMF has a pretty big impact here as well. A lot of people have been arguing that the high to low mass end ratio of the IMF changes a lot as you go to high redshifts. Yeah, there's a lot of caveats, a lot of room for exploration here. I'm talking about this in context, just limiting it to kind of the simple picture because still early days with James Webb. All right. So with that information about, how rapidly the light to mass ratio changes, let's think about the different nature of very UV bright and very UV faint galaxies at high ratios. Again, the UV luminosity function, the number density of galaxies as a function of UV luminosity, has long been our way of measuring, characterizing, the high redshift universe. So really the next step is to begin characterizing the demographics of the bright end and the faint end. At the bright end, as I told you before, we have a lot of objects with very strong nebular line emission, very young continua. These are objects currently experiencing a burst of star formation. That's not surprising because whenever you are experiencing a burst of star formation, you in turn have large light to mass ratios. So it's not a selection effect, it is an intrinsic nature that whenever we have very bursty star formation histories at high redshifts, in order to get the brightest galaxies, the kind of main pathway that happens is you have a relatively massive galaxy that has experienced a recent burst. Okay, so you kind of are forced into that situation in order to get a galaxy way over here that we were able to characterize with Spitzer, et cetera, et cetera. And things like G and Z11 that are being found at very high redshifts. This class C12 object that was very UV bright that is now by spectroscopically confirmed. A lot of these seem to show signatures. You can ask Peter about this too, that they are, kind of this burst mode systems, basically. Okay. And then as we go down fainter in the UV luminosity function, I mentioned before that we were seeing some of these extremely strong line emitters, but then we were also seeing objects that, appeared to be consistent, at least, with a recent rapid decline in the star formation rate on 5-10-ish million year scales. Okay. So what's happening there is you're bouncing both intrinsically low mass objects to higher luminosities because they have experienced a burst, but then you're also taking relatively high mass objects and then pushing them to lower UV luminosities because they have experienced a strong decline in star formation rate. Okay, so at the fainter end of the luminosity function, we just have a broader mix of both bright or things that have experienced an upturn in star formation rate and things that have experienced a downturn in star formation rate. Okay. Let's think about all this in context of reionization. What does it all mean? So again, galaxies we think are the primary source of all, the bulk of hydrogen ionizing photons for reionization. The galaxies here, the bright end, or at least those with the recently rising star formation histories, they are going to be very efficient at producing hydrogen ionizing photons. Okay, and that is basically all of these things at the bright end. You get a high number of recently formed O stars. You get a lot of hydrogen ionizing photons produced as a result. Whenever we move fainter down the UV luminosity function, we have some of those starburst galaxies as well, but then we have objects that have formed very little, if any, hot massive O stars. So they're going to be very inefficient producers of hydrogen ionizing photons. So at the faint end, you have some objects that are very inefficient at producing hydrogen ionizing photons. How many? So my studies have largely been in context of a statistical sample. I like to work with hundreds of objects if I can assemble them to get some kind of summary statistic constraint on what's happening here. So this is the plot for this kind of point. This is the fraction of objects with relatively low hydrogen ionizing photon production efficiencies. So Sion less than 25.3 for those of you who are familiar with the literature there. It's not super low, it's lowish. The point, though, is that here at the bright end, MeV minus 20, there are extremely few galaxies with inefficient ionizing photon production, less than 5%. Once I move to MeV minus 17, these are Hubble deep field type objects, I now have about 30% of my Lyman break selected galaxies that are inefficient, relatively inefficient at producing hydrogen ionizing photons. Okay, so this is important for reionization. We cannot ignore the napping galaxy population whenever we try to convolve our UV luminosity function with, psi ion and then the ionizing photon escape fraction. Okay, if we want to piece together this self-consistent picture of galaxy assembly and reionization, we have to account for the fact that towards the fainter end, you're going to have more objects that are not forming hot massive O stars, and they're not producing large numbers of hydrogen ionizing photons. What that means for ionizing photon escape, that's a much more complicated question. I'm looking into that. I don't have much to say on that because I'm not super confident in my conclusions yet. It's a lot of caveats. Yeah.
So I assume this comes from the flexible star formation acidity field.
Correct.
So how much do you think this quantity is driven by the sort of the continuum, and how much do you think it's driven by the lines,
Yes.
right?
Yep.
So, yeah, I mean, I'm wondering sort of this parameter, how degenerate it is with the other parameters in the fit, right? And is it mostly the line, the parameters that dominate the line, the polarization modeling, or the better population for production?
It is, so in the data, it is being driven by and large by the equivalent width of the nebular emission lines. If a galaxy has a very red continuum slope implying a strong dust contribution, it will self-consistently correct for that in the output. Right, this is important to it. This number is coming directly from the SED modeling out by Beagle. I am not like inferring an H alpha equivalent width and then directly scaling that to an ionizing photon production efficiency. Beagle tells me what this number is whenever I fit the photometry, and that's what I'm using here. Does that answer your question?
Yeah, but that part of the spectrum in the acidic fit,
Yeah.
right? Like you don't have photometry there because the line will break, I guess.
Right.
It's driven by the lines mostly.
Yeah. Just the same way people do it at redshift 2, right? You take some H alpha luminosity, right, and then you Balmer correct the dust absorption. Yeah.
Yeah. So I guess the question is, what are you think are the parameters, or how much? What are I mean, any acidic fit has degeneracies between parameters. So what are those sort of the main things that you think might be degenerate with this?
I mean, I think metallicity is going to be a non-insignificant contributor. Dust attenuation, my assumptions, right now I'm assuming an SMC scaling relation because that's been shown to better reflect what happens whenever you get about below a fifth solar metallicity, at least at lower redshifts. So most of the galaxies, are consistent with that and expected to be less than a fifth solar metallicity. Then, nebular properties that we're inputting into the model, right? So everything to do with ionization parameter, right? You can shift ionization parameter. If you go to really high ionization parameters, you'll get weaker lines, even though the galaxy is producing the same number of hydrogen ionizing photons. That can have a significant effect. Whether the photometry actually allows us to constrain, or rule out extremely high ionization parameters, that's something I haven't convinced myself of, because something like the Beagle photoionization models is quite different than the FSPS models, that Charlie Conroy has generated whenever you get to very high ionization parameters, because they have different definitions for what ionization parameter is. It's complicated. Yes. Yep. It could be. Again, we can, this is basically the end of this part of the talk, so we can go to that part if you would like. Let me find that real quick. So if we want to explain the objects with young continua and weak nebular emission lines, what can I do? So this is the constant star formation history fit, assuming no ionizing photons are leaking out, that tension that I was mentioning earlier between these 2 points. Here's what I get with the constant or flexible star formation history. Sorry, again, assuming no ionizing photons are leaking out. It all works. This is constant star formation history, now allowing the ionizing photon escape fraction to go up to 80%. Beyond that, then you start getting density bounded conditions and things don't. You need to make different assumptions on your nebular emission treatment. So that's why we capped it at 80%. But basically what we find is for objects like this, you need a very high ionizing photon escape fraction, 70%. Here again, 70%. So this is the kind of regime that you need to go into in order to explain these galaxies in context of a constant star formation history. Ignore lots of the plots, sorry. This is what needs to happen then for the demographics of your ionizing photon escape fraction. So the bright objects are shown with red curves, intermediate luminosity objects with orange curves, the faintest objects with the blue curves. So the faintest objects need to, by and large, have ionizing photon escape fractions 30-ish% or higher. That is very high, right? And I worry that if you were going to make that assumption, and then also with the constant star formation history, these things are producing a lot of ionizing photons, then maybe we end reionization too early. So this is, again, I haven't fully quantified that. That's work in progress, but this is part of why I'm not comfortable with this interpretation. Yes.
Do you understand why the models allow for F-0 prefer higher metallicity at the same time? Don't have much lever on there.
Yeah. Let me.
No, it's not just metal lines, it's hydrogen lines. So in some sense, you have the hydrogen line gives you escape, but it also, like, O3 H beta is in part a function of metallicity and in part a function of the escape fraction. So is it essentially down to those two photometric bands, their ratio gives you the lever arm there, you think?
Yeah, I think so. I think what might be happening is I know the O3 to H alpha ratio does start changing as you go to very high ionizing photon escape fractions. So it might be because we're pushing basically at this density bounded regime that I was mentioning before that maybe something interesting starts happening there, and that's changing the O3 to H alpha ratio in such a way that it requires higher metallicity. I haven't looked into that, but that's just maybe my first pass guess at that. So maybe this is just better reflecting the, I mean, it's a poor fit overall, right? I mean, you got best fitting chi-squared here. That one's pretty okay, I guess, but yeah.
Yeah, I mean, it's consistent, the top one's consistent with basically 0. The bottom one, though, is still performing statistically a higher. Anyway.
Yeah,
move on.
it is interesting. Yeah, thanks for pointing that out. I haven't looked at that before. Okay, where are we at? All right, let me try to get through the rest of the talk in enough time. All right, so taking the next steps. So this is where really my next project is going to be on this topic. It's going to be using this data from cycle 2 observations that we'll hopefully get in June, October. We're still working with SCSI on scheduling there. But the project is, let me stare really deep, single pointing at a single lensing cluster, Abell S1063. This is one of the simplest clusters. So lensing modeling, magnification is relatively easy to do. It's all very hard. Relatively easy to do. It works really well at redshift 7. You get high magnification factors at redshift 7 just because of the caustics. And in principle, this will allow us to push down to intrinsic UV luminosities, MUV minus 12 at redshift 6 to 7. Okay, so now, with Abell 2744, the uncover, all previous JWST data has kind of been limited to around MUV minus 16. Well, maybe go 4 magnitudes fainter than that in this sample. I don't know if it'll be statistical. We'll just have to see what the data says. But regardless, we're going to get a lot more very faint galaxies than we've ever had before with this data set. And we can begin characterizing, the ionizing photon production efficiency, star formation histories in the same way that I have in the previous paper. Again, bearing in mind all the caveats we've been discussing here. So that's where I'm going next. So let me now tell you about the stellar masses of these galaxies. It is important to recall that whenever galaxies experience a burst, their light to mass ratios go way up, right? And those hot massive O stars that have just formed are going to dramatically outshine, the A stars and everything that had formed previously. Perhaps, I mean, it depends on the relative scale of the star formation burstiness. But if that burst amplitude is very high, you'll just have this dramatic outshining effect, where all the lower mass stars that have formed in previous generations just get hidden away by the light from the recently formed OB stars. And what that means is that we kind of have this fundamental limitation on our ability to constrain the stellar masses of these high redshift galaxies. You can get dramatically different stellar masses depending on what you assume happened the star formation history a long time ago, okay? So this rightmost plot is kind of demonstrating that. If I assume some kind of bursty prior or a constant star formation history for some of these galaxies, the difference can be of order a factor of 50 in the most extreme cases. Okay, and that's just a limitation on what the light from this galaxy is telling us. Okay, this is the most extreme case. These are objects with the strongest nebular line emission. Okay, the most objects where it's just completely dominated by O stars. But this does remain kind of a caveat to quantifying stellar masses at high redshifts. Okay. Yeah. Well, and the continuum.
That's but the continuum at that rate. So broaden out the coverage. Why don't you go ahead with this? I know where you're going with the high redshift, two bright galaxies, right? So that's what we're.
Not necessarily. No, I really just want to emphasize that stellar masses are very hard to obtain at these redshifts.
You're going to use the the ratios of lines to continuum in a narrow band, that's absolutely true. If you do a wider band, then you have continuum from the A stars again. And
But
that's-
that continuum can still be outshined by the OB stars that have recently formed, right?
Radiation is coming out of the
And not in the rest optical. The nebular continuum emission from the recently formed OB stars in the rest optical will outshine the continuum emission, the stellar continuum emission from the A stars. Okay, okay, all right. So here are the objects with the largest stellar masses that I found in JADES at redshift 6 to 9. So out of all 756 objects, I found 13 with a stellar mass greater than 3 by 10 to the 9 solar masses. Okay, and the most massive one had a stellar mass of around 1 by 10 to the 10 solar masses. And this is using star formation histories, assumed star formation histories that allow for the most amount of star formation at early times. Okay, so I can hide away all the stellar mass and the light that from the stars that most recently formed. Okay, it's effectively an upper limit on the stellar masses in these galaxies. The most massive one is 1 by 10 to the 10. We're not seeing any evidence of these overmassive star-forming galaxies at these high redshifts in the JADE sample. Okay. All right, but what if we want to find truly massive galaxies in the early universe? I would argue that what you want to do is you're going to go to very wide areas. Okay, so as I mentioned at the beginning of my talk, my thesis was oriented around characterizing reionization-era galaxies over wide areas. It's kind of this nice little data set where I can begin kind of quantifying the, well, first discovering if there are any, but then also constraining the number density of these extremely massive galaxies at early times. So there was this object that I found 2021, I think it was, had an extremely red rest UV slope. Okay, this is just ground-based ultravista data in the cosmos field, and then here's my Spitzer IRAC, and it suggests that there could be a very, very strong Balmer break in the system, implying a stellar mass well exceeding 10 to the 10 solar masses. Okay, and it resides, as I said, in the cosmos field. We now have several ALMA line detections, just undeniably proving this thing is at redshift 6.85. There's no way around that anymore. But what is this thing? So here are detections of this object in the MIPS 24 micron band and the Herschel Spire 250 micron band. What that's telling us is that there's very hot dust emission from a hyperluminous AGN in this originally selected Lyman Bright galaxy over the cosmos field. We then have detections in several radio facilities, VLA, LOFAR, Meerkat, 144 to 3 gigahertz. Here's the radio SED for those of you who are interested, but it all is consistent with emission from an AGN jet, okay? Synchrotron emission from an AGN jet. So let's piece everything together. Cosmos has just so much data in that field, so I can really piece together a nice full X-ray to radio SED, and this is what you get. It implies a stellar mass of order 10 to the 11 solar masses, still TBD, we'll get there. Extreme obscured star formation, the dust continuum luminosity in the ALMA band was extremely bright in this thing. Again, I'll get to that. But then we also have this radio loud, hyperluminous, extremely obscured AGN in this object, okay? So here's this object in context of other quasars. These are everything at redshift greater than 5 whenever I publish this paper. Black is Lyman Bright galaxies, blue are extremely UV luminous quasars that people have found like over all sky surveys. Red is this object in cosmos called COS 87259. And then this orange thing here is this submillimeter galaxy that's composed of 2 subgalaxies, and they're each shown as separate points there. But the main message here is that this object that we found in 1.5 square degrees of the sky has among the brightest C2 luminosity of anything we've ever known, among the brightest C2 line of anything we've ever known, and among the most luminous dust continuum emission of anything we've ever known at redshift greater than 6.5. It was found in the 1.5 square degree cosmos field. These extremely UV luminous quasars, they're usually found over several tens of thousands of square degrees, okay? So something's really weird here. But effectively, this object is a highly obscured version of an extremely UV luminous quasar at high redshifts. So MEV minus 27 is what we're approximating would be the unobscured UV luminosity of this object. And it, assuming Eddington ratio for the bolometric luminosity here, we're inferring a black hole mass that's a bit above 1 billion solar masses. So all consistent with the properties of these extremely UV luminous quasars that we know at high redshift. But again, why did we find this? How did we possibly find this in the 1.5 square degree cosmos field? This thing has been overlooked for a long time. The data has been there for a long time, by and large. But people have been finding these sub-millimeter galaxies, thing like the orange, over 20,000 square degrees, and they found one at this redshift, right? What happened? So we're trying to understand this better. I took some high-resolution ALMA data, and here's what we get for the dust continuum luminosity. So, the dust continuum is kind of extended. It's 2 sigma contour, but then there's this extremely bright, compact emission, basically unresolved. And if I take that peak surface brightness and I convert it to a dust surface density, I get greater than 700 solar masses of dust per square parsec. You can make some assumptions on your gas to dust ratio, a factor of 100. It's kind of common in the literature. And then you can infer an H1 column density of order 10 to the 25 per square centimeters. This is Compton thick obscuration of the AGN. But what's important to realize here is that Compton thick obscuration is not necessarily coming from a nuclear torus around the AGN. It's coming from the host ISM. This is cold dust emission. That gas is presumably just in the ISM of the host galaxy. So presumably this is a very massive galaxy. It's a very dense, compact, cold gas that is resulting in this heavy obscuration of this hyperluminous AGN, something that is akin to the most UV luminous quasars that we've ever found at these redshifts. Okay, so the main message is that maybe, whenever you get to high redshifts, these galaxies are smaller. Most massive galaxies form in such a way that leads to this very dense ISM, and that can result in these very high column densities. This has been predicted in simulations, though kind of in a qualitative way. Quantitatively, it's still a bit muddy. But yeah, so I'll just tell you a little bit here about the Cycle 3 program that got approved to study this object. So one of the main things is studying the host galaxy. We want to find out if it really is of order 10 to the 11 solar masses. It's never really been possible to actually constrain the stellar masses of these extremely UV bright quasars before, just because the host galaxy is just outshined by the AGN. And even if you take really complicated PSF subtraction and techniques, people have been working really hard on this. It's still very challenging even with James Webb. But since this object is heavily obscured, I don't have to worry about the AGN emission in the rest optical, I hope. I'll find out. But if that's the case, then I'll get some really nice constraints on the 2D, spatial distribution of stellar mass surface density, star formation rate surface density, dust attenuation, fold that in with all the ALMA data. So it'll be a really nice first detailed study of the host galaxy of one of these very early, extremely bright quasars. Another program that I'm working on is called MEOW, the MIRI Early Obscured AGN Wide Survey. This was a almost large Cycle 3 program that got approved. It's conducting relatively deep MIRI imaging in the goods fields. And the idea here is that you can use the MIRI imaging to identify moderate luminosity obscured AGN at high redshifts. So Gene will be working on constraining the black hole accretion rate density as a function of redshift going out to very early times. What I'm interested in is once we find those obscured AGN, I want to characterize their host galaxies, find out if there's any correlation between concurrent bursts of star formation and recent AGN activity, so what. So that's my talk. Thank you all for your attention and your questions so far.
We had some questions, but any others?
I already asked several, so I'll let you go. Thank you. This was fascinating. Okay, so one last question, which is perhaps you don't care to sort of comment at this point, but you showed some mass estimates.
Yeah.
So if you were to take your luminosity function and turn it into something more like a mass function, and then think about sort of this idea you have of sort of a duty cycle on burstiness as a function of mass. Have you looked at that at all? Do you see any trends there that are interesting?
Haven't looked at that at all yet. So I would think the biggest challenge right now, if I can go back to one of these plots. So even with JADES, right, we were really kind of like complete in the UV luminosity sense down to about here, right? Everything is kind of over here, right? And if I'm telling you that the light to mass ratios change by more than a factor of 10, right? I think we're heavily limited still in the samples that we have to things that are currently going through a burst, right? We're starting to identify maybe the most extreme cases of things that aren't undergoing a burst. But my main point is like, I really want more constraints on what's happening over here before I even attempt that kind of a modeling, because my intuition says that if I try that now, I have so limited information on what's happening in the far more abundant phaeton that like, I just don't know how many objects are scattering into the regime of which I'm actually now complete at with the existing data.
Do you think the lens sample will give you
I-
anything on that? The statistics are gonna be harder.
Yes, that's the thing. I hope that's probably the best way I can put it right now. I think that my hope is that that survey will actually constrain where the UV luminosity function turns over. And I think that will be a pretty nice handle on like what's happening with the star formation histories there as well, just given what I've told you about how the UV luminosity is so strongly dependent on where things are in a burst or after a burst. So there is modeling that can be done there. And I think maybe we can start attempting it once we have that cycle 2 data. But yeah, I think it's still very early days and there's a lot of work to be done.
So you sort of avoided making a strong statement about it, but this that you're sort of looking to stellar masses and variation in light to mass ratio due to burstiness makes you think that these claims for like extremely high mass, almost unexplainable high masses at this very, very early epochs, could be explained with just star formation history and burstiness, or do you think those claims are robust?
So I think the burstiness is mainly affecting the most UV luminous objects that we found at high redshifts. I think that can all be explained with bursty star formation histories. The FIRE team put out a paper demonstrating that in the context of their framework, their modeling framework, they fairly accurately predict the luminosity functions that people are measuring from JWST data at the highest redshifts, even at the bright end. Whenever you're talking about the most massive objects, something like Ivo Labe's paper, right? Those objects have been shown to either be at the wrong redshifts or now these things that people are calling little red dots, which appear to be some kind of heavily reddened but not completely obscured AGN. So I wouldn't call those star forming galaxies. People are trying to model them with star forming solutions and just, it's very weird. I haven't seen a model that like actually explains all of the data that exists on these things. So until that's the case, I'm not willing to say that there's any tension with cosmology or anything like this.
Thank Brian.
Thank you.